our recent approach based on my joint work with Victor Buchstaber, how one can try to describe the orbit space of the Grassmannian Gn2 by the action of the compact torus using some hyperplane arrangement that somehow naturally appears here. In general, we have the following situation. So we consider complex Grassmann manifolds, Gnk, which are k-dimensional complex subspaces in Cn. And one considers coordinate-wise action of the compact torus, on a complex space. And this action induces the compact torus action of the Grassmann Gnk. This action is not effective. Diagonal fixes all the points, and we get that torus Tn minus n acts effectively. And here arises the notion of complexity. The complexity is just the difference between halves of the dimension of the manifold and the dimension of the torus, which acts effectively on the manifold. And in this case, we have that this complexity is greater and equal than 2 whenever is k greater and equal than 2 and n is greater and equal than k plus 3. So in particular, when k is equal 2 and n is greater or equal 5, we obtain that the action is of complexity greater and equal to. And the complexity really means somehow it is also related to the complexity of the problem, because when the complexity D is equal to 0, we get a class, actually in general, we get a class of manifolds to which fit the toric manifolds, quasi-toric manifolds, and whose orbit space can be combinatorially described. The complexity 1 is, widely known. It's much more known and much widely studied. And I think Anton Eisenberg today is going to speak about that. And here, the complexity 2 and higher complexity is much more complicated. I just want to say that here, Tn action, compact torus action, extend to the algebraic torus action of Gnk. And the problem here, which we consider, is somehow to describe the combinatorial structure and algebraic topology of this orbit space. Which are homeomorphic because we have these duality diffeomorphism. And my talk, I'm going to present the new results, which are related to the description of the orbit space through the hyperplane arrangement, but mainly the techniques, a lot of techniques, and the statements I am going to use from the following paper. The three last paper by Gelfand-Serganova and Gelfand-Serganova, Goreski, and McPherson was somehow fundamental papers for for us to deal with these problems, as well as the paper by Kapranov, from which consider these problems a little bit from algebraic point of view. And in this direction, we I may say recently published 3 papers. In the first 2 papers, we actually considered mostly the action on the Grassmann manifolds G4-2 and G5-2, while in the third paper, we somehow established theoretical foundation for the action of the torus Tk on M2N manifolds. What is here somehow when I said that in this here we are going to provide a description of the orbit space, we will use 3 main ingredients in describing the orbit space. First is, we call it soft chamber decomposition of the hypersimplex delta N2. Namely, we consider a hyperplane arrangement in Rn, which is given by this set of planes, and by the planes xi is equal to 0 and xi is equal to 1, which are actually to which actually belong the facets of the hypersimplex delta N2. Then we consider the phase lattice of these hyperplane arrangement and consider intersection of these phase lattice with interior of delta n2. Why I consider interior, it will be clear later, because because everything here can be done inductively. Then the second ingredient we use here is the spaces of parameters. There are some topological spaces that can be assigned to any chamber, say soft chamber, from this decomposition of the hypersimplex delta n2, and these spaces actually parameterizes the C star orbits. In other words, the part of C star orbits that sits over the chamber C using the moment map. And the third notion we use here is the universal space of parameters. I mean, that's a little bit a new notion which we earlier introduced, and it will be clear during the talk what it is about. To start with, I just want to recall that using Plucker embedding of the Grassmannian Gn k into the complex projective space, so using the Plucker coordinates, one can embed Grassmann in the complex projective space where n is n over k. And using that, there is standard definition of the moment map on the Grassmann manifold, which each element L maps to the linear combination of the vectors lambda I, where lambda I are n-dimensional vectors which have at k places 1 and n minus k places they have 0. And these places where we have 1 are indexed by the set I, and the Pi, Al are just Plucker coordinates for the element L. Then it is the image of this moment map is just convex skull of these vectors lambda I, and it is known to be hypersimplex, polytope hypersimplex. Delta and k, although it is defined in Rn, it belongs to the hyperplane where the sum of coordinates is k, so its dimension is n minus 1. And what is important for us here is that the moment map is Tn invariant, so it means it introduces the map from the orbit space to the hypersimplex nk. And the first thing we want to pay attention here is that, so we have the action of the Tn, we have the compact, the moment map which is invariant, and how these are related to the automorphism of the Grassmannian Gn k. And there is first, like a remark, lemma, that we notice that if we consider those elements, those automorphism of G and K, which commutes with the canonical Tn action, then this subgroup is a just semi-direct product of the torus Tn minus 1 and the symmetric group, which acts by permutation of coordinate when n is not equal to k. And when n is equal to k, we have this product with Z2, where Z2 actually comes from the duality automorphisms between GNK and GNN minus K. Now, when we ask about the relation with the moment map and the automorphism of the Grassmann manifolds, so in other words, we consider those automorphisms for which there exists, say, combinatorial isomorphism of the hypersimplex delta nk such that the following diagram commutes. So what are these? So it means that, in other words, in other words, for such combinatorial automorphism, isomorphism f bar, the pre-image by the moment map and the origin and the image will be the same. Then it turns out that that if we consider such automorphism on G and K, for which there exists this combinatorial automorphism f bar for delta and k, then the subgroup are the same. It's in the n is not equal to k. It's this same direct product, and this is this we have this set 2 coming from the duality automorphisms, and the corresponding combinatorial isomorphism of the hypersimplex delta and k are just for Tn minus 1 it's I mean obvious that it is identity, where for an element from Sn it is just a permutation of the coordinates in delta and k, where for duality isomorphism it is given by the like a central symmetry related to the point which all coordinates are 1. So as a corollary of these two things, we have that when we consider when we consider this moment map nu hat from the orbit space to the hypersimplex delta and k, then the pre-images of the points, which belong from delta and k, which belong to the same orbits of the group Sn are equal, are homomorphic, and in the case of n equal to k, the pre-images of these 2 points are homomorphic. So somehow and in this way it reduces the as it will be clear later, it reduces this problem of somehow description of the orbit space, because I mean first it naturally appears if we have these moment map mu hat to ask what are the which points have the same pre-images. The next construction we use here is actually these we consider these open sets Mi. This is the standard, actually the standard charts, the atlas for Mi, which are given by those elements from G and K which have the height Euclid coordinates non-zero. So in other words, if we write L as a n times k matrix, then the k times k minor determined by the I is non-zero. These sets are open, and the dense set in G and K. G and K is union of these Mi. Each Mi contains exactly one fixed point, and the here fixed point are just k-dimensional coordinate subspaces. And now if we consider YY, the complement of Mi in G and K, one can define the strata, the stratification of G and K. Now, if sigma is some subset of k-element sets of the set 1 to n, then if we consider the intersection of all Mi, where I is indexed by sigma, and intersection of all Yi, where I is indexed by an element which is not its sigma, and intersect these two sets, if we get that this set is non-empty, we say that such a set is a stratum. This is the first example here is the main stratum, namely if we consider set sigma, sigma, this is the set of all k-dimensional subsets in sigma, then we get here intersection of all Mi, and it is an open and dense set in G and K. What are nice for this strata is that any two strata, the intersection of any two strata is empty. The strata are C star n invariant, and they are of course then Tn invariant, and G and K is the union of these strata. So in this way, one obtains the stratification of the Grassmann manifolds. This is not a new notion. I mean, the stratification. We just see here in a write this in a little bit different language, so one can generalize it on an arbitrary manifold M2N with a torus section for which are given some atlas which is appropriate in this way. These strata are not nice. They are no open, no closed, and in algebraic geometry is known that the geometry is not nice, that they may have singularity as bad as possible. What first we proved earlier, I mean, and this is easier to verify, that if we apply the moment map to the strata, then it will be interior of the polytope P sigma, where P sigma is convex half of these lambda I, where lambda I the vertices of the hypersimplex delta and chi, delta nk, where I belongs to sigma. And so P sigma is just some polytope over the vertices of delta and k, and if some polytope P sigma in delta and k can be obtained as the image of as the image of some stratum, then we call such polytope an admissible polytope. So an admissible polytope actually can be, one can imagine as arbitrary polytope over the some subsets of vertices of some hypersimplex delta and k. As I said, this new notion is not new. We just wrote it down in a little bit different language, but this notion of the strata coincide with the strata of Gelfand and Serganova, or together Gelfand and Serganova, Goreski, McPherson, where actually they provided three equivalent definition of the strata. And one definition is that the strata consists of all points from G and K, whose closure, algebraic torus orbit closure, which is a toric manifold, maps to the same polytope. From this description, which is actually follows from Atiyah-Guliman theorem, convexity theorem, it follows that any face of admissible polytope is an admissible polytope in case of G and K. And then, from this lemma, it follows that the main stratum, which is intersection of all charts, it maps to the interior of the whole hypersimplex delta and k, while the fixed point maps to the vertex. And actually, we have the bijection between the fixed points and the vertices of delta and k. And so it immediately follows that all faces of delta and k are admissible polytopes. Now, what we proved earlier in one of these papers I listed is that when we take a stratum, then all points have the same stabilizer, as well as compact, as well as algebraic stabilizer. So we have a torus which acts freely on W sigma, and we have a moment map from W and K. This moment map, it decomposes in the following way, since it is invariant. And what we proved in our one of our earlier papers, that this mu hat, which maps this orbit space of the strata to the interior of P sigma, is a local trivial fiber bundle whose fiber is an open algebraic manifold. So since P sigma is contractible, we obtain that the orbit space of any strata is homeomorphic to this direct product. And for such space F sigma, for such algebraic manifold, we say that that is a space of parameters for W sigma. And actually, from the description of the strata, equivalent description by Gelfand and Serganova, we actually see that the space of parameters of the strata is just the orbit space of the strata by the action of the algebraic torus. So to summarize, what we have here is that the orbit space of the G and K can be stratified into these orbit spaces, and each of these pieces is homeomorphic to this direct product for some polytope P sigma and some space F sigma. Moreover, since the main stratum W is a dense set in G and K, it means that the orbit space of the main stratum is a dense set in G and K Tn, so there is compactification of this product because the orbit space of the main stratum is homeomorphic to this product for some open algebraic manifold F. So in other words, there exists compactification of this product, which not directly, but whose quotient, to say, may give some quotient may give the orbit space G and K Tn. And having this in mind, our goal was to describe P sigma, which appears here, F sigma, and some compactification, and to find, say, appropriate compactification for F such that for which this homeomorphism realized. Because I mean, here we have that this orbit space is homeomorphic to this union, but the problem is how this how these pieces are glued together. It's a problem how to glue together these pieces in order to find the orbit space, and somehow we found that the solution for this is to find some compactification of the space of parameters f of the main stratum, which will help us to somehow to describe this gluing. So now I will speak about these things in a case of the Grassmannian Gn2. So Grassmannian Gn2, the admissible polytopes is delta n2. It belongs to the to this hyperplane. So the dimension of any admissible polytope is less equal than n-1. First thing we prove here as a new result is that if dimension of admissible polytope is less equal to n-3, then this admissible polytope must belong to the boundary of delta n2. So in other words, it has to be at the face of delta n2. I mean, from the polytope theory, it's easy to see, even directly using Grassmann manifolds, that the boundary of the hypersimplex delta n2 is just union of n copies of simplices, n-2 dimensional simplices, and union of n copies of hypersimplexes n-1, 2. And also earlier we show that the pre-image of the boundary of delta n2 is just the union. Over here we have the n copies of CP n-2, and over these simplices we have n copies of the Grassmannian Gn -1, 2, and actually we can describe all these embeddings of all these CP n-2 and all these Grassmannians in Gn2. So in other words, when we want to describe the orbit space, the orbit space of CPN -2 is very well known. This is one dimension less. So somehow we can proceed by induction and now restrict ourselves only to those part of the Grassmannian Gn2 which maps by the moment map to the interior of Gn2. Now, I'm going now to say about admissible polytopes. So if a admissible polytope P sigma of n-2, it may be it may intersect interior or belongs to the boundary. If it belongs to the boundary, then it is either this simplex, either it is some admissible polytope, either it sits here and it is some admissible polytope for Gn -1, 2. So now, so we can restrict, as I said, to the case when we consider admissible polytopes which intersect the interior of delta n2. Such admissible polytopes we call interior admissible polytopes. And the first result in this direction is that the family of interior admissible polytopes of dimension n-2 are actually are those polytopes which I obtain by the intersection of delta n2 with the following planes. So here we have the sum at least two elements, and the sum and the number of elements is less equal than the integer part n/2, because the sum of all coordinates is 2, so we have a symmetries. We can describe actually the set of these polytopes, n-2-dimensional polytopes more closely. Namely, symmetric group Sn acts on the set of these planes P by the permutation. So if we fix one plane, if we fix those planes which contain the vertex lambda ig, vertex lambda ig is the vertex which has which has one at the place I and G, then these planes are of the following form. The number of these planes is as follows, and the Sn orbit of these planes is the set of all these planes which give n-2 dimensional orbit with stabilizer S2 times Sn-2. So this group acts on the set of these planes which contain the fixed vertex. So we can decide the number of irreducible representation for this action S2 times S minus 2 in this settled plane. The number is this, and the dimension for n odd are this, and for n even are this. This how enables us to describe actually or n minus 2 dimensional polytopes, to describe the numbers and the number of vertices. And as a corollary, we obtain that any n minus 2 dimensional polytope has n minus p vertices, and the number of polytopes which have these vertices is the numbers is as follows. It is n over p for n odd and n over p for n even. So in this way, practically we completely describe all n minus 2 dimensional polytopes. So now examples when we consider, say, G42, Grassmann G42, n minus 2 dimensional polytope is a dimension 2. Using this theorem, we obtained that we have just one generating S4 generating polytope, which has 4 vertices. Altogether, we obtain 3 polytopes, and they are given by these planes. In G52, we consider 3-dimensional polytopes. Also, the set of 3-dimensional polytopes has just one S5 generators with 6 vertices. Altogether, we obtain 10 set polytopes. And I mean, the one example which is a little bit more complicated is when consider 4-dimensional interior polytopes. We have 2 generating polytopes. They have 8 and 9 vertices, 15 and 9 polytopes, and they are given on this way. And actually, they just correspond to the S2 times S4 action on C7, which has 2 irreducible summands. So in this way, we completely describe n minus 2 dimensional polytope. As for n minus 1 dimensional polytope, we obtain also in this combinatorial and geometric description, actually any n minus 2 dimensional polytope is either delta n2, either it is the closure of intersection of the interior delta n2 with the collection of the half spaces of the form. So we consider all possible collection of the half spaces of this form, and taking care that if we fix some collection, if xip and xiq contribute to that collection, then ip is not equal iq. So this is, in this way, we obtain n minus 1 dimensional polytope. For example, when we consider G42, the 3-dimensional polytope are delta 42, and the polytope defined by the half spaces. This is the number and the number of vertices. For G52, these are 4-dimensional polytopes defined by these half spaces. These are the number and the number of vertices. And say for G62, these are also the way how we can, these are the 5-dimensional polytopes are given by these half spaces, and by intersection of these half spaces, these are their numbers and the number of vertices. So the second is we want to describe the space of parameters, as I said, of the strata. The first is the main stratum. If we consider the main stratum belongs to any chart. Here charts are parameterized by Mij, where ij are some numbers from 1 to n. And if we consider the chart M12, so it means that 2 times 2, first minor is non-zero, and consider the local coordinates in this chart, then the main stratum can be described by this, by this family of equations, where the parameters Zij prime belong to CP1A, where it is CP1 minus these 3 points. It follows from this condition, the condition that no one of Zi and Wj is 0. Then from the Plücker, since we have the Plücker coordinate satisfies some relation, from the Plücker relation, we obtain that these parameters of the main stratum satisfy this relation. So they satisfy some cubic equation. And so the space of parameters of the main stratum, as we really defined it, it's the orbit space of the main stratum by C star n, and we get that it actually this open algebraic manifold, which sit in CP1n when n is n minus 2 over 2. So this is the space, this is how the space of parameters of the main stratum can be described in a chart. Of course, it does not depend on the chart because of the action of the symmetric group. Now, if we have an arbitrary stratum which belongs to this chart, then the stratum is defined by the condition that some of its Plücker coordinates are non-zero. Say, if these Plücker coordinates are zero or non-zero, if these Plücker coordinates are zero, in the local coordinates, it translates in this way. So actually, if we write down, so we can write down as the same equation is for the main stratum, but this condition will allow us that the space of parameters may be also the point 1, 1. So the spaces of parameters of the strata are just some algebraic manifolds. What we prove here in a case of Gn2, in a case of Gn2, we prove that if P sigma is interior polytope of dimension n-2, then the space of parameters is a point. Actually, when considering the space of parameters, we should consider only the polytope of dimension n-1. And now the third ingredient I said here, which we need, is a so-called universal space of parameters. And I said the universal space of parameters actually we introduced it in our paper in Moscow Mathematical Journal published last year. It's some compactification of the space of parameters f of the main stratum, actually, which realizes in some sense that the closure of this is Gn2 over Tn. So somehow it's some space which is compactification of f capital such that the orbit space Gn2 over Tn can be obtained from the direct product delta n2 times that compactification f using some relations. The universal space of parameters is axiomatized in this space for 2nk manifolds. It's not short definition, so I will skip it here. But I will say that the universal space of parameters really exists, and I will say here how we construct it for the Gn2 one construction, and it is space which is explicitly described for G52, this space in this paper. Then by Klemyatin, one can find his paper on archive. It is proved that actually the Chow quotient by Kapranov of the Grassmannian Gn2 satisfies all our axioms requirements for the universal space of parameters. So, but so this notion is related to the, somehow actual problems of algebraic geometry, because it is Grothendieck-Knudsen compactification of n-pointed curves of genus 0. So we've described here universal space of parameters using representation of the space of parameters of main stratum in the chart. As I said, it can be represented by this collection of by some subset in CP1A on N, which satisfies these cubic relations. What is the idea for finding the universal space of parameters? As I said, when we have a stratum in the chart M12, then this stratum is defined by this condition. And then using this, if we put in this equation, since the main stratum is a dense set, so if we put in this equation the condition of the arbitrary stratums, so we put that the sum coordinates zi, some wi are 0, then we will get that some Zij prime are 0, 1, 1, 0, or if in both sides we have 0, we can get that that Zij, we have here singularity. So Cij prime can be an arbitrary element from CP1. So what does it mean? It means that using this equation of the main stratum, we can assign the new space of parameters f tilde to the stratum W sigma, but this assignment should not depend on the chart W sigma. So if we take, because we want to assign to W sigma, and when we say assigned, assign means that we want to find some compactification of the space of parameters of the stratum such that this assignment, as I said, using the equation of the main stratum will not depend on the chart. For the GN2, we proved that if we consider the closure of the space of parameters of the main stratum in CPN, which is just intersection of these cubic equations, we obtain that the space, if we consider the space F, which is obtained by blowing up of this space F bar along the submanifolds, where the submanifolds are defined by this condition, then any homeomorphism of F, which is induced by the coordinate change, extend to the homeomorphism of F. So, because if we consider coordinate change between these two charts, this coordinate change extends to the homeomorphism of the space of parameters of the main stratum. And in a case of such a space, this homeomorphism of F extends to the homeomorphism of F. In other words, this assignment I was talking about will not depend on the choice of the chart for the stratum we consider. And then we prove the theorem that the space F obtained in this way is the universal space of parameters for GN2, so it satisfies all the requirements we put previously. For example, when we consider G52, then G52, we obtain that in this way that the universal space of parameters is just blow up of this surface at the point 1, 1, 1, 1, 1, 1, and actually for this we proved in our earlier paper, and this blow up is unique. Say when we consider G62, then according to this theorem, F is the blow up of this F bar along the following submanifolds. Now we have here 4 submanifolds, and the dimension of F bar is 3. Each pair of these 2 submanifolds intersect in this point. So here, of course, arises the question of blow up at this intersection point, and I mean, it's not claimed to be unique, this blow up. So in the universal space of parameters in this way is not claimed to be unique. Up to now, we have not proved that. So to summarize, so when we prove that there is universal space of parameters, so to each stratum can be assigned in this way virtual space of parameters, and this virtual space of parameters does not depend on the chart. Whichever chart we fix, we will going to get the homeomorphic spaces of parameters. And now, if we fix a point into interior of delta N2, we can consider X tilde. It's the union of all virtual spaces of parameters where for all admissible polytopes which contain the point x. And the nice result here is universality theorem, which we prove that somehow it explains why this space is a universal space of parameters, that X tilde is equal to F for any X from the interior of delta N2. And when we consider two virtual spaces of parameters that contribute to X tilde, then they are disjoint. So I want to say, when we consider we have spaces of parameters which are somehow in some sense real, and to each point X we can assign also the union of the spaces of parameters, the union of the space parameters through the whole polytope which contains that point X. And in general, this union of the spaces parameters are not homeomorphic, are different for different points from X inside. But for the virtual spaces parameters, they are same. Okay, And now, what I said we want to do is now, since we have these we describe n-2 and n-1 dimensional polytopes through this plane, we consider the hyperplane arrangement. The hyperplane arrangement defined on this way. These are, as I said, the planes that define n-2 dimensional polytopes in delta n2, and these are the planes which contains the facets of the hypersimplex delta n2. And we consider the phase lattice for the arrangement A, and the intersection of this phase lattice with the interior of delta n2, and the elements of these decomposition we call so in this way we get some decomposition for the interior of delta n2, and we call it soft chamber decomposition. And from what we did previously, it follows that this chamber decomposition of delta n2 coincides with the chamber with the composition given by the intersection of all admissible polytopes. So we have these chamber decomposition of delta n2 into the soft chambers. And from the results of Gilfand-McPherson from 1987, it can be proved that whenever we have using these results, it can be proved that whenever we have the 2 points from the same chamber of this chamber decomposition, the pre-images in the orbit space are homeomorphic. So to each chamber C, we can assign some topological space Fc, which we call the space of parameters of this chamber C. If dimension is C, the chamber is its real chamber. If it is maximal dimension, then we proved earlier factor, not in this language, but we proved that this space Fc is a smooth manifold. To summarize, so it means whenever we have some say chamber from this chamber decomposition, then there exists canonical homeomorphism from the pre-image of this chamber in the orbit space and the product of C with Fc. And moreover, Fc, since the main stratum maps to the whole delta n2, Fc is just compactification of the space of parameters of the main stratum given by the spaces F sigma, where sigma is such determined by those polytopes which contain C. So we have this decomposition of delta n2, and we consider the pre-images in the orbit space. For G42 is somehow the simplest case, and for G42, these Fc are all homeomorphic, and they are homeomorphic to CP1. Already for G52, that is no more the case. I mean, for different chambers C, the pre-images are not homeomorphic, and that's the reason why the orbit spaces, I mean, we proved that the orbit space G42 by T4 is just sphere S5, while the orbit space is G52 over T5 is sphere S, is rational homology sphere S8, but the homotopy is equivalent to much more complicated space. Using this universality theorem, one can also as now, if one consider this chamber composition related this chamber decomposition to the virtual spaces of parameters, one can conclude that if we have some chamber from this chamber decomposition, and this chamber is actually obtained as intersection of all admissible polytopes which contains it, then the corresponding virtual spaces of parameters does not intersect. And now CIS-F is a universal space of parameters, and one of the requirements for the universal space of parameters is that it is union of all virtual spaces of parameters, and that for all virtual spaces of parameters there exists projection to the space of parameters. We obtain that the following corollary, that when we fix a chamber, the union of all virtual spaces which correspond to this chamber is the whole universal space of parameters. So it follows that it is defined the projection from the universal space of parameters to the space of parameters of any chamber by this way. We take some y, this y belongs to some f tilde, to some f tilde, since to unique f tilde, since this is the joint union, and for this f tilde, since f tilde are defined in the universal space of parameters, we have these projections. So now, to summarize, we can form so-called, we call it weighted lattice for Gn2, phase lattice for Gn2, which is actually this product, and this union, interior of Gn2 is a union of these cells from this product, is the joint union. Each of these pieces is homeomorphic to its pre-image by the moment map in the orbit space. So we obtain that the pre-image of the interior of delta N2 is just the union of these, and it is homeomorphic to the union of these pieces. And now, of course, it raises the question how these pieces are glued together. But just to say that the group, as symmetric group, acts on this decomposition. It permutes the chambers. So it means if two chambers can be, there is permutation from which maps one chamber to another, then it follows that then from the relation between the moment map and the action of the torus and the automorphism of Grassmannian, it follows that these spaces are homeomorphic. So it means that the group Sn acts on this weighted lattice. So it means that it reduces significantly reduces the number of these factors in this lattice. So altogether, when we consider the orbit space, it is pre-image of the interior, union n copies of this orbit space, union n copies of this orbit space, CPU by n minus 1. When we consider, so just to say, when we here over the interior, we have the universal space of parameters. Here we know that the space of parameters are points, so this is not a problem. But here, the universal space of parameters its own also arises, and we can here prove that universal space of parameters for Gn-2k, which k is one of the copies of Gn-2 embedded into Gn2, is just the restriction of the universal space of parameters Fn2 to some say coordinate subspaces in CP1n. So what we can consider, then we can consider this space delta n2 times f, and consider the map which to each 2 points x, y, this here, consider point x, y, we have unique chamber that contains the point x. For this chamber, it is defined the projection. So this belongs to the c times fc, and hc minus 1 gives us the point from Gn to n. And we prove, as in the, in the case, what we did for G52 over T5, that G is continuous surjection and that the orbit space is homeomorphic to the quotient space of this space by the map G, what we wanted for the beginning. Thank you.
All right. Thank you very much, Svjetlana.